This is a balanced three-phase circuit. Although between small n and capital N there is an open circuit, but the open voltage between them is zero. So they can be connected by a short line without changing any other branch variables in the circuit. Then we can use single-phase method to solve the circuit. We draw phase A circuit here. The effective value of the line voltage is 380 volts. Suppose UAB phasor as this. According to the phase line relationship of the star connection, we know UA equals this. Strictly speaking, 380 over square root of 3 doesn't absolutely equals 220. 220 is a round value. The phase current of phase A circuit is this. The load is with a star connection, so phase A current equals line A current. So we get IA. Based on symmetry, IB lags IA 120 degrees, so IB equals this. Thus, we've completed the analysis of the whole circuit. This is a three-phase, three-line circuit. The source and load are both with delta connection. We have two methods to solve the circuit. Firstly, we can see that UAB and this impedance consist a loop. UBC and this impedance consist a loop. And UCA and this impedance consist a loop. The three loops can be solved separately, so we can get this. Suppose UAB as 380 with 0 degree. By substituting the phasor with numerical values, we know this. The load is with delta connection, so it satisfies the phase line relationship of the delta connection. The magnitude of IA is square root of 3 times IAB, and IA lags IAB 30 degrees. So IA equals this. According to symmetry, we know IC leads IA 120 degrees, so IC equals this. Besides this method, we can also apply star-delta transformation and phase line relationship of the source to transform the circuit into the one with two star connections, and phase A circuit is like this. UA is 220 with negative 30 degrees, and 1/3 of that is 33.33 with 30 degrees, so IA equals this. The source and the load are both with star connection, so phase A current of the load equals IA, the line current. According to symmetry, we know this. Thus, we've completed the analysis. You can find this. The essence of these two methods are the same. We suggest you to use the second method because in actual condition, it's not common that the source and the load are both in delta connection. In most conditions, it's a mixed connection. Let's look at this circuit. The source is with the delta connection. The load 1 is with star connection with the impedance on the neutral line, and the load 2 is with a delta connection. In this condition, we often transform the load 2 into star connection with a star-delta transformation and draw phase A circuit with single-phase method. Since the value of Zn doesn't affect any other branch variable in the circuit, so it can be short-circuited. Then we can draw phase A circuit. Suppose line voltage UAB as 380 with 0 degree. So UA equals this. According to the magnitude and the phase angle of Z1, we know it equals this. 1/3 of Z2 is this. From this SSS circuit, we can easily get IA. This is the phase A circuit of the star connection, so phase current equals line current. IA equals the underdetermined line current IA. Thus, we've completed the analysis of the whole circuit. After solving these exercises, let's summarize the analysis of the balanced three-phase circuit. Firstly, the connection of all sources should be transformed into the Y connection, and the connection of all loads should be transformed into the Y connection due to phase line relationship. The impedance on the neutral line of the load can be ignored or short-circuited. Then, according to the series and parallel connection of the loads, we draw phase A equivalent circuit, which is shown in the figure, and calculate all the branch currents of phase A. The load is with Y connection, so phase A current equals line A current in actual circuit. Then we know the line current of phase B and C due to symmetry. Well, this is the end of this lecture.